When you type a prompt into a large language model, it feels like having a conversation. You write a sentence, and the machine reads it. But that feeling of understanding is an illusion. Deep down in the hardware, these systems are entirely blind to the alphabet. They cannot process letters or words. They operate exclusively on pure mathematics, interpreting sequences of numbers. To cross that gap between human language and machine mathematics, your text has to be converted. Every memory limit and API fee is measured in tokens, the essential bridge translating human language into computational data. Let's look at exactly how this translation pipeline works. Imagine feeding a standard complex sentence into the model. The immediate instinct is to assume the system reads that sentence word by word. But modern large language models rarely treat a whole word as a single unified piece of data. Instead, they use a process called sub-word tokenization. A complex word like unbelievable is physically fractured into structural blocks like un, believe, and able. Punctuation marks are stripped away, becoming isolated units. Even the empty space between blocks is categorized as an active structural piece. This granular fracturing solves a massive processing problem. If the model had to assign a unique identifier to every single word in existence, the system would collapse under the weight of the dictionary. By breaking words down, it can handle extremely rare terms using familiar pieces. It also gives the system the ability to interpret entirely new or made-up words. It simply analyzes the known root components that make up the new word. Sub-word tokenization takes the vast variations of human language and cleanly compresses them into an efficient, finite set of modular building blocks. But we still have a problem. Those broken-down syllables and punctuation marks are still made of letters, which means the machine still cannot process them. To fix this, the model relies on its vocabulary. The vocabulary is a massive internal index containing tens of thousands of known text blocks that the system is trained to recognize. This table shows the exact translation process. The tokenizer consults the vocabulary index and maps every single text token directly to a permanent, unique integer ID, turning I love dosa into 101, 567, 998, and 42. This resulting sequence of integers is the true format of the data flowing into the model. That vocabulary index serves as the absolute boundary of the AI's comprehension. If a text chunk cannot be mapped to a number in that index, it simply does not exist to the machine. Once you understand how these tokens are created, you can see how they dictate the physical memory limits of the entire system. Every model has a context window. The context window is the strict maximum capacity of tokens the model can hold in its active memory at one time, combining both your input prompt and the machine's generated response. This diagram shows what a strict context window looks like on a large document. A 4,000 token limit does not equal 4,000 words. Because of the unpredictable sub-word fracturing seen earlier, 4,000 tokens might cover far fewer actual words, leaving anything outside that boundary discarded. Pushing a larger sequence of these numerical tokens through the model's architecture requires exponentially more computational power from the host servers. That heavy demand for computational power translates directly into slower generation times for the person waiting on the other side of the screen. It also dictates the strict financial realities of running these systems. Most API providers charge users a fee based specifically on the number of tokens processed. An API, or Application Programming Interface, is a service letting external software communicate with the model. These providers usually price their compute power per 1,000 tokens. Because of these hard memory and cost constraints, application developers have to actively design around them. They often employ retrieval-augmented generation, which is a technique that fetches relevant information from an external database to improve the accuracy of the AI's response. To do this, they take massive documents and break them down into smaller, digestible chunks. Those individual document chunks must be precisely measured in tokens to guarantee they fit comfortably within the AI's strict context window constraint. If you want to build scalable applications or write highly effective prompts without hitting invisible walls, you have to abandon word counts entirely and start thinking strictly in tokens. We have successfully traced how human text is chopped up and converted into a clean sequence of integer IDs, but those raw numbers still carry absolutely no inherent meaning. For the machine to actually comprehend what you are saying, those IDs must be thoroughly transformed into embeddings. Embeddings are dense, high-dimensional vectors that give the machine an understanding of context and relationships. That transformation is exactly what we will cover in Episode 3. Here at Knowledge Equity Partners, our goal is to provide practical, contemporary knowledge to enhance daily efficiency and keep you ahead of the curve. If you found this breakdown valuable, please subscribe, like, and share the video to keep the quest for knowledge high. Then click the link to watch Episode 3 and join us for the conclusion of the data journey.